Get started here. Mike just decided not to introduce me because I think by now most of you probably know who I am, but for anybody that snuck in late, hi, I'm Brian, and this year I'm the chair of this mess. So I feel a little bad here because if you read the talk description, you kind of got a little bit of a pig in a poke. I actually did a dry run of this talk at COPI a couple months ago, and it turned out that as a general introduction to Async I for nobody that had seen the concepts, it was way too ambitious. I had about 2/3 of the outline. It ran about an hour and a half, and folks that hadn't done Twisted stuff were thoroughly confused. So it scaled back quite a bit. So if you're like a really killer developer, and you're looking for some deep dive into it, it's not going to happen. You probably want to wander over and find Brandon Rhodes' S-Trace talk because it'll be really killer. So with that said, this is a general introduction to Async I, both in the sense of Async I, the new library that's in Python 3.4, and into sort of the concept of asynchronous I/O in general. It's something that I discovered, and I've been doing a little Twisted stuff off and on for a few years now. I was kind of surprised talking to some of the COPI folks. Most people don't ever sort of delve into this, so there was a lot of conceptual stuff that needed to be teased out. So with that, just a little bit more about me, other than I'm chairing PyOhio this year. I'm sort of the classic jack of all trades. I've been working in IT for about 20 years, and if there's a position, I've held it. I've worked in phone support, QA, I've managed those groups, I've done product management, run a couple developer groups, worked at a couple Fortune 500s, a few small, closely held businesses, 2 startups, and was a partner in a consultancy for a while. So it's all over the place. And at every one of those jobs where I actually coded, until I came to Python, I think I learned just enough to be dangerous and attack the problem at hand and move on. So I've probably written bad things in a dozen languages that you all would shudder to go look at this point. My first Turing complete language that I ever wrote in was PostScript, actually. I ended up working on a QA team that was arguing with the developers about the output from a desktop publishing application. And the best way to win the argument was to dump the print screen and learn how to debug it. So that's how I actually ended up teaching myself to write software. And that will mess you up. Stack-based, reverse Polish notation, it's, yeah. So, currently, I am the CTO at Ola Healthcare Technology, which is a... Okay. Yeah, I heard. I think they're working on it on the board. Is it? Are we good now? Okay. Okay. So, yeah, we are working on some solutions for medical image sharing outside of the sort of walled garden of the hospitals. Anybody that actually works in healthcare technology, there's a standards body working on exchange standards, and they have something called XDS-I.B. We are actually not doing that because friends don't let friends do soap. And I also do a little consulting on the side. We take a lot of software where I am the principal windmill tilter. So let's talk about asynchronous I/O in general. A form of input-output processing that permits other processing to continue before the transmission has finished. So basically, we're just saying, hey, I'm waiting on bytes. Typically, when we're talking about async I/O, it's there is, in theory, asynchronous I/O calls to disk I/O in POSIX systems, and none of them actually really are. It just turns out the caching is so fast, most of the time it doesn't matter. So we're typically talking about waiting on the network, and if you think about something that is not asynchronous in the way we're talking about it, and that is single-threaded. If you're waiting on bytes, you can't do anything else. So we're just talking about how do you do something else while you're waiting on the bytes. When people start talking about this, they start talking about things like concurrency and parallelism, and it adds to the confusion a little sometimes because sometimes folks are Using those things, right, these are development terms. We think we have a common language that we're talking in, and sometimes we are not. So in the general sense, when you say concurrency, you're just talking about multiple computations happening at one time. So formal definition up there for computer science, several computations are executing simultaneously and potentially interacting with each other. And then parallelism, which is sort of a subset of concurrency. Many calculations are carried out simultaneously, operating on the principle that large problems can often be divided into smaller ones, which are then solved concurrently. When we sort of are talking about networking applications and we use that stuff just in everyday conversation, what we're usually kind of talking about with parallelism is task parallelism, right? I've got some kind of problem that can be distributed. Usually it is processor bound, so we're going to break it up into chunks and distribute it around and do work on it. And the kind of concurrency that we're talking about here is not useful for that. So what we're really talking about, a more useful definition when you're talking about this kind of concurrency, is to say you've got individual steps of multiple tasks, and you're going to execute those in an interleaved fashion. So think about a web server, and I've got 10,000 connections. I'm dealing with the bytes coming off of those connections. I have to do something with them. I'm going to interleave that so I don't block and deal with only one connection at a time while everybody else sits around and waits on me. You can assume that only one statement is executed at any point in time. So typically when we talk about this kind of concurrency, we are not doing any kind of task parallelism. Yeah, you can be, but conceptually you want to think about it as you're slicing this stuff up. So even though you're handling a lot of things interleaved, at any given time you're really only doing one thing. But, okay, your code doesn't necessarily, any given piece of that code has no guarantee what task gets to run next. So you just, all this stuff is running, and at any point in time, you can't really guarantee who's got control from any other piece of code's execution context. Okay. So when do you need it? Handle thousands of connections, or tens of thousands of connections. So this is the classic for those folks who are working in web development, you know, why Nginx is starting to supplant Apache, especially at the front end, because if you're just running an event loop and using this kind of concurrency, you can run one process and handle tens of thousands of connections on the same box. You can get an order of magnitude more than running a combination of processes and threads using Apache HTTP. So those are the kind of problems that we're talking about solving. Also, the ability to sort of scale horizontally. So when you're doing this kind of concurrency, each little task tends to be its own separate thing. So I can handle 10,000 on this machine. I can slap a proxy in it and spin up another copy over here and handle 20. You don't have a lot of shared state. The other thing is if you do something like this threaded, you can scale vertically, right? I've got a bunch of threads running, but I can make the box bigger. But if I need to add another box, and I've done this threaded instead of this kind of concurrency model, that doesn't necessarily help you, especially if you've got some shared state stuff. A lot of communication between network nodes. This is a networking technique, so in addition to the client-server thing, if you've got a lot of stuff that needs to cross-talk to each other, it's a useful tool to have. Warning signs that you probably don't want to be doing this. You need to integrate with things that block. Remember, when you're doing this kind of concurrency, conceptually you're single-threaded. Now, in reality, there's usually multiple threads, and you've got stuff doing little background things that need to be dealt with. But the actual main execution context for everything that's happening is one single thread. So if you do something silly like read some data off of a network and pass that into the start of a Fibonacci sequence, everything else is going to sit around for a while till it finishes. So if you're integrating with third-party code that does stuff that's processor intensive and tends to block, that can't run asynchronously or be broken up into smaller chunks, bad idea. That's especially bad if they block in Python code, because we'll talk about this in a little bit. A common pattern for dealing with third-party blocking code is, even though we're not using threads for our main concurrency model, if I got to deal with something that blocks, I kick it off into a thread and let that thing deal with it and wait for the answer to come back to my main loop. Because of the global interpreter lock, if you've got something over there chewing up computation, your event loop still is not running, even though you've thrown that thing into another thread. So even if you're going to do things and dispatch them out to threads off your main loop, those should be things that are coming out of libraries where they're C and will release the lock. So you're coding your blog, you know, unless you're Guido, you probably don't need to worry about enough hits to do this kind of stuff to handle your blog. On the other hand, you know, if you just want to learn, why not? Okay, what about threads? Because you can do and tackle these kinds of problems with threading, right? And that's a common way to do it. I mean, you can do I/O parallelism with threads, as well as processor task intensive parallelism. You just, for every connection, you spin up a thread. And, you know, it can be hard to reason about. And I put the little question mark there because I actually think that in some cases when you're doing this kind of I/O stuff, threads are a little bit easier to reason about than when you're doing a lot of task parallelism because you don't have nearly as much shared state, right? If I'm just spinning off a thread to handle a new socket connection because I'm doing a web server, it's not the same if those threads have all kinds of shared state they have to keep track of because they're working on the same, you know, a chunk of the same problem. So I think that one's probably actually not as bad as everyone thinks. They just kind of toss it out, right? That's why you don't want to do threading. I think scalability is a bigger issue, especially in Python land. OS threads in Python are kind of expensive, so if you're trying to scale something that handles a ton of connections and you're cranking up a new thread for every connection, you're just going to consume a lot of unnecessary resources. And everything you wanted to know about threading in Python, whether you're doing it for I/O or for processor-bound stuff, there's a great paper that came out of a talk by David Beasley. It's listed up there, Understanding GIL. If you just search on Python GIL, that'll pop up. You don't even need to look at the URL. So that's a really great resource, and I highly recommend taking a look at it. So processes. You can do the same kind of thing. You can just spin up a new process. You've got some issues with data sharing. That's gotten better in Python recently, especially in Python 3. There's the concurrent module, so it's a lot easier. You can sort of write something that looks like threaded code and then just do it in processes. So you're not using like the subprocess module to manually spin up subprocesses and keep track of the pipes and do all that work yourself as much. But it's got different scaling issues. It actually scales better horizontally than threads because it's easier to spin up processes on a second box or a third box or n boxes. But when you're just trying to get the most out of a single box that you can for this kind of I/O stuff, that's even heavier than threads, right? I'm spinning up another application for every connection. Does anybody been, you know, remember back when Apache was just entirely pre-fork and that's exactly what it did? You know, you didn't get nearly as much out of it as you do now. So historically, there's already been some work prior to Async I/O on solving these problems in Python. And coroutines are a biggie. And you'll often hear these other terms tossed around for them: greenlets, green threads, tasklets, microthreads. It kind of depends exactly on how they're implemented or the project that they're part of. What these basically are user space threads. They're not real operating system threads. They're not preemptive. The OS does not schedule them. They're cooperative. So basically, your greenlet or coroutine or whatever you want to call it gets control, does some work, and then it needs to yield control back for something else to be able to do work. And that's why I talked a little bit before about if you're integrating third-party blocking libraries, that gets in the way of this, because in the middle of one of these green threads, if you grab something that blocks, then nothing else actually gets to advance work. And so the whole idea of green threads is you do a little chunk of work, and then you let go so somebody else can do a little chunk of work, and so on and so on. But your application is essentially responsible for scheduling that. So implementations, probably the three best known, are Stackless, Eventlet, and Gevent. Stackless is kind of like granddaddy. It's actually a separate Python interpreter that, in addition to having a Greenlit implementation, actually does that in a way that it does not push stuff on the call stack that it normally would, and it's actually out in memory space. Now, the thing about working in Stackless is it is a separate Python interpreter. So if you write stuff specifically for that environment, you've got to use that interpreter. You can't switch back to the regular reference C interpreter. So, is it? Thank you. Can you hear me now? Okay. So actually, and then the other two, Eventlet and Gevent, and actually to an extent, Stackless. So Eventlet and Gevent are just libraries that you can add to the regular C Python reference implementation. And they use coroutines. They're built on top of libevent or later libev. And the nice thing about these is that basically you can do asynchronous I/O and write normal-looking imperative code, which is kind of the knock against some of the other players in this space in Python. So, but one of the problems with that, just being able to spin up Eventlet or Gevent and write, once again we're going to talk about blocking and the whole thing that they must yield, is that there's all kinds of stuff in the standard library, right? So that does block. And so if you spin something up and you start working in one of these imperative libraries, and you have to deal with that. And so typically the way that they deal with that is this. Basically, there are special non-blocking versions of a lot of stuff in the standard library that you can pull in. So at the top we see from Eventlet green import URL lib2. And what that basically guarantees is that things like the socket module get forced to be called in asynchronous mode, and there's some wrapper code that deals with it so it won't block, and it kind of abstracts that all away. The other thing that you can do is Eventlet import patched something. And this would be like if you have a third-party library that you're pulling in usually, and by doing that import patched, it makes sure that anything from the standard library that the third-party library pulls in actually does those magic imports at the top. And then down at the bottom there's total evil, which is sometimes there's nothing you can do but call monkey patch right at the top of your application, which basically tries to force that patching on everything. And I just, this is one of the things I think that, and I'm not knocking these projects because they're great and they've allowed people to do some great things, but whenever I see monkey patch, or monkey patch all in the context of like a Python application, that just kind of weirds me out a little bit, right? Right? Explicit is better than implicit, and then we've taken basically a whole bunch of code and kind of swapped some stuff out under the hood. It's almost like I shudder to say Ruby magic. So the other common way of handling these are with asynchronous event loops and callbacks. And those are kind of four of the biggies that were in the space before Async I came along. And there are some others, but async core is basically the old way of doing async stuff in the standard library. Run away. Basically, I don't think that code's been really messed with in about a decade. So it's very low level, it's not useful, you have to do a whole lot of work to build anything around it. It's kind of like if all you had to do regular network in Python was the old low-level socket stuff that the higher-level sockets module wraps. So I just put it there because in the older Python distributions, it is still sitting in the standard library. So Tornado is mostly aimed at web application stuff. I'm going to skip Twisted for a second. Diesel is actually, I think, a pretty interesting framework if anyone wants to Google it and run out and take a look at it. It was kind of built to solve a lot of the problems that Async I was working on before that came out. And it actually is pretty well written code. The thing is it just never really developed a big community. So now I think that now that there is a blessed asynchronous I/O library, that one's probably not going to stick around for very long. And then Twisted is kind of like the granddaddy. And basically Twisted solves that whole issue of monkey patching by not dealing with that imperative style or trying to wrap a bunch of stuff in the underlying standard library. It does its own thing. It's got its own event loop that talks directly to the underlying select. So whether it's select or poll or epoll or KQ, whatever select library it's dealing with, so it bypasses that whole lib event libev thing. And it uses a sort of callback, and if you've ever worked in a language that has futures or promises or something like that, idea called deferreds. And so I sort of probably jumped ahead. So and down at the bottom, that's kind of the big knock on Twisted, is you need to grok their funky way of doing callbacks and deferred. So this is a real little simple piece of sample code here. This is just Python 101. We've got a little app here. At the top, we've got show mail, which takes a string and prints it. And then we've got something that waits. So we've just got a little standard blocking imperative app here. While true, we see if this file exists. If it's not there, we sleep. We come back, we open it. If it's there, we open it, we break out a loop, and we call show mail to show it, yada, yada. If you write that in Twisted, you've got to sort of invert some things a little bit. We still have a show mail, but now wait for mail returns this Twisted concept called a deferred. So you return the deferred, and then when the file is actually there, you essentially, when you come down to the bottom, you fire the callback of the deferred. So all the way down at the bottom, when you call your wait for mail function, you actually have to handle the deferred it's going to return, because it's going to return the deferred instead of the result. Then you have to add show mail as a callback routine, so that this thing will all run the way it's supposed to do. And in this simple example, that's not too terrible. But if you imagine that you're dealing with code where you've got, function calls nested 4 or 5 or 6 levels deep, if you're a relatively proficient developer, that's not terribly hard to follow. The other good thing is that all your error handling works the way you expect it to. If you're doing this in Twisted code, it starts to get a lot harder to reason about following all the callbacks and jumping back and forth. And you've also got to run a simultaneously set of errorback chains to handle all the errors, because exceptions will not do what you expect them to do. And if you leave an uncaught exception, it's almost always useless in trying to figure out where things really went wrong. So, then there's one last thing here, is that none of these things work well together, because they all sort of assume I'm the event loop that's running concurrent events, and if there are other threads or things running, there's some housekeeping, or maybe I deferred a processor-heavy task out to a thread. So basically, if somebody built this really cool thing for Twisted over here, and somebody built this really cool thing for Eventlet over there, and using those two things together would solve my problem, that's just too bad. So, the solution: one ring to rule them all, and in the darkness bind them, usually to a network socket. So, Async I basics, like a lot of the stuff we're talking about, runs in an event loop. Just like Twisted, it actually picks the best I/O call for the platform, epoll, KQ. By the way, another thing that I didn't mention real quick is, in all of these, only Twisted or Async I work decently in a Windows environment. And the reason for that is that both of them can actually use Windows IOCP model to deal with the networking layer, whereas basically everything else only uses the old crude select model on Windows. So all of this stuff, if you move it to Windows, it is just terribly slow and inefficient. So, okay. Then some other things that they were sort of shooting for when they built Async I/O. One, and preferably only one way to do async in Python. Just in case you're able to implement other event loops as abstractions on top of Async I/O. So the idea, one of the ideas for Async I/O is, for instance, the Gevent people could actually go implement the interface of Gevent on top of the Async I/O layer instead of directly on top of libev. And then you'd be able to actually use those things together. Whether or not that'll really happen, I don't know, but they're allowing for the possibility. The other thing is if you want to replace that low-level event loop, you can actually swap that out too. And there is actually somebody working on doing that. I'm not even sure if there's a real reason other than proving that you can. It's called the Rose Project. Just a brief aside, if you want to go read about all of this, the PEP 3153 and PEP 3156, the Python enhancement proposals, they're probably some of the most interesting discussions that I've ever read in a PEP. Especially when you get Guido and the guys that did Twisted arguing back and forth about what an asynchronous I/O framework should look like. A lot of smart guys having a lot of interesting discussion and a fair bit of agreement and disagreement. So there's a lot of good stuff there. So, and I'm running a little longer than I wanted, so I'm going to have to speed it up here a little. Event loop. So the event loop, basically what it does, it pulls for data. So I've got, network socket. Let me poll and see if I've got data to act on. If I do, I run callbacks against those polls, and then I check to see if it's time to poll again. If it is, I go ahead and poll. If not, I wait a little bit and then poll, and I just repeat ad nauseum. So in Async I/O, there's a bunch of functions that deal with the event loop. So if you need to actually get a reference to the loop, Async I/O get event loop. If you actually do have one of these alternate implementations, you can actually set event loop and pass a loop in. You can actually even create multiple copies of the same loop structure. So the underlying loop that runs on Async I/O, you can actually set things up so you actually really have 2 or more event loops running in threads, which is something you really can't do in any of the other implementations that I'm aware of. And then you can call new event loop to generate a new event loop. So base event loop is basically the underlying class that for all event loops. So, and these are basically the things that you can call to run a loop. So you can just run forever, which really runs forever until it actually catches some kind of interrupt. You can run into a complete and pass in a future, which is like Async I/O's version of the deferred we just talked about in Twisted. You can stop the loop, you can close the loop, and you can check to see if the loop is closed. And then callbacks. So callbacks basically interact with the event loop and allow you to actually stick callbacks. Usually you don't use this a lot in Async I/O code. There's higher level abstractions that you'll start building things out of. But you kind of sort of see what this stuff does here. You can kind of get an idea how some things start to get constructed under the hood. So base event loop call soon. So basically if you call soon and hand it a function, it sticks that on a queue. And as soon as the loop comes around to the call soon queue, everything that's in that queue gets executed in order. So boom, 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 boom. So when something to get called back off a loop as quickly as possible, it's call soon. And there's actually a thread safe version of it if you're running multiple loops, or if you're actually calling into the event loop from another thread. Call later. You'll see that a lot when you start looking at example code. Call later is one of the 2 common ways to simulate waiting on something elsewhere. A lot of times when you see sample code teaching you things like Async I/O or Twisted, they'll want to introduce something that provides delay. So that simulates, hey, I had to wait on something that came, from the other way around the world on the network. And this is sort of in a way almost like calling time sleep in a straightforward imperative piece of code. And then call at is something that is a little different in Async I/O that I don't think it existed in Twisted. They do have call later. Basically, you can go ahead and essentially set a time, and the function will run at that time. Now, all of these things are not exact, because like when I call later, all I'm really guaranteeing is it will wait at least that long. It may wait longer. It depends what else is running on the loop, what other callbacks have to be fired, what data needs to be handled. If you go back to the beginning, we talked about, when you're talking about this kind of concurrency, one thing that you can't guarantee is the order of operations. So, and then there's a function to get the time. And the reason for that is that sometimes the event loop time is not the same as the system time. The way they keep track of time for efficiency purposes can be a little less granular than just calling like time from the system. So basically, if you need to get that while working inside here, you've got a function that calls that. And then a couple more things that are just here so you can kind of get an idea of how some stuff works at the low level. You have add and remove reader and add and remove writer. And basically, this gives you a way to add something that a file descriptor, and when it has data, it will fire the callback and hand it the data plus whatever additional args that you passed in there. And the same with writer. So, all right, code. Let's go play just a little bit here. Okay, I'm not going to run through all these just because I'm running a little longer than I wanted, so we're going to just cut the chase. And this is just a real simple example, the call later, callback call, and how it works. So basically, we're going to go ahead and run loop call later, and we're going to run it with a 2-second delay and print and this print and repeat function. And then what we're going to actually do is go ahead and fire it with call soon to start the process up. So, and since we passed print and repeat into call later, what we're essentially doing here is we're setting up an infinite loop that'll just run and annoy you. So. But that'll just sit and print hello world forever for 2 seconds. And I mangled that a little bit, so just running back over it real quick. So yeah, so print and repeat fires the call later callback, and we pass a copy of itself back in. So every time it fires, it calls later on itself again and just keeps running forever. Oops, how did that get in there? Okay, generators. So before we go on to the next part, we actually need to take a little quick side trip into generators, because the coroutine model of Async I/O is built on generators and some new stuff that's in Python 3 for generators. So what am I doing here? Oh, I know what I'm doing. Forgot to play the slideshow. There we go. Okay, so so here's some procedural code, and pretty simple. Get odds. We're going to create a list. We're going to run over a range, and we're going to do a little modulo arithmetic. And if they're odd numbers, we'll append them to the list, and then we'll return the list. And then down at the bottom, we can use for to loop over that result and print it out. So generators sort of provide a syntactic sugar to create an iterator. So rather than building that list and then having to iterate over it, you can just sort of next and get a value, next and get a value. The other sort of cool thing about them, though, other than just that idea of I don't have to use an iterator object and build a class and do all this stuff and create my next routines and all that, is that under the hood, right, every time the generator runs and it releases control to the caller, there's some state being saved there, and then it comes back into that again. So the function just doesn't go away when it gets to the end. So when I run down here and I say for I in range blah, check the modulo, do yield I, that releases control, it comes back out to my function at the bottom, and then that state gets maintained, and then I enter back into the generator again. And so you can actually start playing around and do some neat things with that later. For instance, now you can actually send data to the generator. So this is something that not a lot of people know. So I've got print me here and a while true loop, and in my yield statement, normally you're, in Python 2, if you've used generators, you're used to seeing things on the right side of that yield, right? It's almost sort of like a return for the generator. But if you put something on the left side of that yield and you send something to the generator, that variable will actually captures a reference to that item, and you can do stuff with it. So you almost sort of get a simple coroutine out of it, right? So I create printer print me. You actually have to call next on the generator if you're going to send stuff to it once, so the generator advances to that first yield. In some cases, you can actually do a send none as well. So, and then the other thing that you need to know about is yield from. So look at a couple generators here, just really simple. For n in that list, we yield n. For m, we yield m. And if you create a generator and run that, you'll get A, B, C, D, E, F out of it, right, when you iterate over that generator. You can actually sort of refactor that out. So now I've got two generators, one for the first list and one for the second list. And then I can write a third generator that iterates over those two generators and spits out the result. Okay. There's a new yields from statement. I think it came out in 3.3, but it might have been as far back as 3.2. But it both supplies some syntactic sure to do that, and there's also some weird edge case stuff that breaks down when you start chaining generators together that the yield from deals with a little bit better. But that's getting really esoteric for an intro thing. So if you're really interested, go read the PEP on yield from and dig through the source code. Oops. Come on. Okay. So we're just going to play with send generator real quick here because it kind of shows the concept of being able to send stuff. Oh, wrong one. That's the busted one. Sorry about that, guys. I'm running late now. I'm getting nervous. This was it, right? Yeah, okay. So yeah, this just shows some of that little bit of coroutine concept when you're dealing with being able to send the data in and also call yield from. So basically we, up at the top here at accumulate, we basically start with a tally, we run the loop, and whatever we send gets handed to next. If next gets sent a none, we go ahead and return. That's another new thing for generators in Python 3. In Python 2, if you actually use a return statement inside the generator, it'll throw an error. Here, it actually does throw essentially a stop iteration error, but there's a way to get the value out. And there's a little magic that if you call yield from on a generator that returns, it kind of swallows the error, and the value of the error gets set to whatever's on the other side of that yield from. So that lets you sort of string this whole thing together. And so what really happens there, you see down at the bottom, we actually go ahead and call a copy of gather tallies, and we pass the tallies list into it, and then we go ahead and run next on that to initialize it, and then we start sending stuff to it. And then when we finally send the none in, what comes back is the accumulated list that we were sort of gathering out there. So. Okay, so coroutines and Async I/O, and basically this will look really familiar because basically coroutines and Async I/O are just Python 3 generators. There is a decorator, Async I/O coroutine, that you should actually apply if that's the way you're using them. But basically, all it does is a little bit of magic. There are a couple other things you can decorate that will turn into a generator if it's not one. And it actually adds a couple properties on there, so you can actually just make a quick test call and say, is this thing a coroutine from your code if you need to know. Yeah, so basically in Async I/O, this is sort of how you do the same kind of looping thing we just did with the callback at the coroutine level. So you actually create a generator. So greet every 2 seconds is a generator because we're calling yield. We're actually calling yield from Async I/O sleep 2, and I put that in red just, remember I said before, a lot of times you're trying to simulate, hey, I'm waiting on something. So that's what you're really doing. In a real application, you'd probably be yielding from yet another generator that was waiting on data from some network socket or something like that. And then you just stuff it on the event loop, run it to a complete, and then you got to finally to close the loop, so you can kill it when you cut out of it. So. Okay. Let's. A little more here. We basically got here just a quick little Echo server and client built using Async I/O coroutines. So at the start of the server, the Echo server itself, we get a generator back. Async I/O start server basically starts a server that handles socket connections, and what it's returning there is actually a generator object. And then that we're also passing in handle connection, which is also a generator. And that generator in turn goes upstream to reader read line. So basically what I just talked about before, when you're sort of asleep trying to simulate waiting on stuff, here we really are actually waiting on some stuff. So we've strung a bunch of generators together. And then over on the other side, same kind of thing. We're just actually, once again, yield from Async I/O open connection, and that returns a reader-writer pair that we can use to talk to the server with. So. Okay. Did it slide? Oh, it got too small. Yeah. Because I killed it. Okay. If I could spell, I'd be all right. Yay. So that's all it really does. It's a classic little Echo server. We send something to the server, it echoes it back. But that's all strung together with coroutines. So basically, if you had a whole bunch of these all firing up, which we kind of do at the end of the demo, which we're not going to get to, I don't think, I'm sorry. So what I'm going to do is go ahead and kind of go through the rest of the presentation, and we'll jump to the last example, which has got a bunch of stuff in it. And then all this stuff will be available online, so we can kind of go poke through the code stuff that we missed. Okay, so futures are Async IO's version of a deferred or promise. Basically, you attach a callback to a future, and it runs when the future is complete. So some code up there. We have a slow operation. We're going to pass a future in. Our slow operation is we're yielding from the sleep thing again. And this time, after that completes, we're going to actually set a result on the future saying it's done. And then we start the event loop, and we go ahead and create the future. And there, at the event loop, we create a task. We pass the coroutine into the task, and then the feature in at the end and run it. So what all happens from that is that generator up there runs, and when it gets done, it goes ahead and sets the result on the future. So now the future is done. The future runs the callback. Which future result? So you call result on future, it hands its result back, and then we print it. So and I want to point that out real quick. Loop create task, slow operation future. So we had a future, we passed it into a coroutine generator, and then created task. Just remember that for a couple slides ahead. So we'll skip over that. And here's remember that. Tasks are basically a coroutine wrapped in a future. So the reason is coroutines, being a generator, don't advance on their own, right? Normally, if a regular generator, if you want it to advance, you actually have to iterate over it. So if you're creating these things as coroutines, and you want the event loop to deal with them and run them, something there has to call next, and tasks are the way you do that. So basically, tasks are a subclass of future, so it creates a future. Remember that? And it goes ahead and schedules that to be run. So the event loop will actually start iterating the coroutine, and when stop iteration happens on the coroutine, then the future callback gets fired. So that's how you sort of start building up chunks of functionality here. Okay. Transports and protocols are kind of the last thing that you need to know a little bit about before you start digging in and doing anything semi-real. The concept there is borrowed from Twisted. It was one of the more interesting things in the PEP discussion between Glyph and Guido. Transport is the communication layer, for example, a TCP socket, but it also can be pipes or a local Unix socket. The protocol is the application protocol itself, so an Echo server, an HTTP server, or whatever it happens to be. So you uncouple those two things, and it lets you mix and match them to an extent. You could write an Echo server that works over TCP sockets and quickly adapt it to use pipes between processes if you wanted to, for whatever insane reason. Transports are not declared as explicitly in Async IO as they are in Twisted, if you're familiar with Twisted. Basically, you just sort of create connections on the event loop, and a combination of the arguments you're passing in and the particular creation that you're calling kind of creates the transport for you. So conceptually in Twisted, you're a little bit more explicit sometimes when you're creating that connection about exactly what it is you're creating. And then protocols are paired with a transport, and that's your base application logic for dealing with data. A last piece of stuff to know is streams, and that's just a higher level abstraction of transport and protocol. So basically, you can call certain functions module level Async IO functions or functions on the event loop, and you get back a pair of stream reader, stream writer objects that say implement a combination of a TCP transport and some kind of socket reader protocol underneath it. And then the methods on the stream object are actually generators. So basically, a lot of times you'll see that construction, you'll call something that creates a stream, and it'll have a little yield from thing in front of it, and what you get back is a coroutine that you can play with. So let's see if we can get here real quick. Okay. All right. So Mike's waving. We're out of time. I'm going to spend about 3 minutes here running through this last little piece of it, just because this kind of starts to sort of put the whole bits together. So basically, here we do have a server that can actually deal with multiple clients. So it's sort of semi-real. And so we have this accept client routine. It's expecting the stream writers that I just talked about getting passed in. And then it will actually create a task that we just talked about. The task will be passed handle client and handle client will be passed in a copy of the reader and the writer. And then it'll also add that to a the task to a client's array so we can keep track of it. And then we go ahead and have this little inner function here that gets attached to the task as a callback. So when we're all done, this thing will actually find the task back in the list. It'll close it and log that it closed. And remember, what we passed into the task was one of our generator coroutines. Here's the definition of that and what it's doing. So it starts out, it actually writes back to the client a hello. Then it actually calls yield from on async I wait for and passes that stream back in. So now it'll wait for data to come back, and when data comes back, that gets returned off of the yield. So it's almost like we call the task calls next, data comes back. We read the data, check to see if we got what we wanted. If we didn't, we log it, yada yada. And then we go ahead and tell the client, we write back to it with the stream writer and say, hey, we're ready. And now we're just going to loop, and same kind of thing. We're just calling async I wait for, yield from against that async I wait for generator, so when it gets data, it yields it back, and then we can play and do stuff with it. So then down at the bottom, we have the stuff we were talking about with the event loop, right? All the way back from the beginning. We actually get the event loop. We actually start the server, and we pass the client task in, and then we actually go ahead and fire up the host and port that we want, and then we run the loop. So when we start the server, it returns a future, so the runs will complete. Says if that future exits, we'll go ahead and stop, even though we told it to run forever. It actually really won't here. And then we'll run through the client code real quick. And same kind of thing. We have a make connection here. Once again, it's a task. So we're going to call async task. We're going to handle a coroutine into the task so it gets scheduled and run. And we're going to have a little callback here that we use. In this case, because this is the client, and we're actually going to use this code and fire up multiple clients, the callback actually stops that instance of the loop. And the handle client generator, we get a reader writer yielded, and then we're going to go ahead and try and let's see. Okay, we're going to connect, and we're going to actually yield from the connection on the other end, and then we're going to wait and see if we get our hello, and if we do, then we're going to go ahead and start sending data. But you see all this stuff starts to get built up by these generator coroutines being strung together and then wrapped into that task, which is kind of like it's a future, or you can think of other languages, or twisted, deferred, or promise. And that's just kind of how the whole thing hangs together. If you run that, it's pretty boring, and you'll just see it echo back and forth for about a minute. So, and since we're short on time, I'm going to leave that as an imaginary exercise and cut to the last couple slides here. Backports, because this only runs on Python 3.4. So if you're interested in playing around with it or even using it in production and you're not ready to go to Python 3.4, you have some other options. Tulip was the original code name for the project. The code was actually all developed under Python 3.3, and part of the sort of constraint was that it needed to run on 3.3. So even though it came out as a 3.4 feature, you can go to the Google Code repository where this stuff was all developed, pull it down, install it on 3.3, and it will run. There's also a backport called Troilus that aims to work on Python 2.6 and greater. Now, the one thing you have to remember about it is we talked about how the coroutines use some generator stuff that only exists in Python 3. So they had to work around that a little bit to get it to work back in 2.6. So some of the coroutine code works a little bit differently, but it's pretty compatible. Another interesting thing, and I didn't talk about this too much, one of the big conceptual differences between Async I and Twisted is Async I is sort of a framework to build asynchronous applications. Twisted is a framework to build asynchronous applications, and a bunch of those applications thrown in out of the box that you can either use or extend or expand. That was deliberately something they didn't want to do with Async I. So the Pulsar project, and I haven't really played with this myself at all, I'm just aware that it's out there. Their aim is to start to fill that gap, right? They're starting to build some of these basic applications, HTTP server, line receiver, things that kind of come out of the box in Twisted that don't really come out of the box in Async I. And then I also want to mention Autobahn, because this is what actually started my journey into poking around at Async I myself. Autobahn is a WebSockets library for Python. If you need to do WebSockets in Python, you should go look at this thing. Autobahn writes the code in Python that does WebSockets testing against about half of the major WebSockets libraries that are out there. So stuff that's out there written in Java and C++ and everything else, when they want to actually make sure their implementation is correct, they're running Python code against it. The original Autobahn ran in Twisted under Python 2. They now have a version that runs under Python 3 using Async I. It also, if you want to use the Async I version under 3 or under 2, it will attempt to actually run Troilus and give you that capability. So if you want to play around with WebSocket stuff or even just get a better feel for a real application running under Async I, that's a great place to go poking about. The source code's well commented and well organized. And I'm sorry I ran over and we don't really have time for Q&A. Probably today I'm a little busy, but tomorrow you want to catch me, we might set up a little open space and be able to talk about some of this stuff further. So thanks for putting up with me.